All right, good morning, ladies and gentlemen. Welcome again back to ICP. We are done with the first 4 weeks of class, so we are now going to be transitioning into chemistry. So we're going to start off today and start off the chemistry unit by talking about the 3/5 states of matter. So you guys should be able to see the PowerPoint up on my screen. If you want to look at the Google Classroom, looking at day 11. Okay, open up states of matter. There's the PowerPoint that I'm going to be going through. Here are your guided notes, and then here's the practice for today. Also, while I'm talking about it, if you have not done your midterm or your other quizzes, you need to be thinking about when you're going to get into the building to get those done. Still haven't received any from anybody yet, so we really need to get done the physics stuff first before you move on to the chemistry stuff. So if you've not finished your physics stuff, please pause this video and get caught up on that first. And if you are finished with that, all right, let's talk about the 3/5 states of matter. All right, so we are going to focus on the main 3 states of matter. Technically, there are 5, and we're adding to that as our understanding of physics and atoms improve. But right now, we're just going to focus on the main 3. So what we need to understand is everything is made up of atoms, okay? The air we breathe, the ground that we're walking on, the chair you're sitting in, the computer you're working on, you, yourself, everything is made of atoms, okay? And the other thing that we need to understand is all of these atoms are in motion. It doesn't have to be a lot of motion, but they are all in motion, and that's really key. All atoms are moving, okay? We're talking, again, on a very, very small atomic level of motion. And the amount of motion that an object has really depends on what state of matter that object is in. So let's get to those 3 main states. So the states of matter are solids, liquids, and gases. Hopefully you've heard of these before. Hopefully this is just mostly a refresher. The other 2 types of matter, or states of matter can exist in matter, are plasma and Bose-Einstein condensates. Now you're not going to get into those unless you get into a more advanced, chemistry class, but plasma is just like a superheated gas, and Bose-Einstein condensates are just something that occurs quite sporadically. In any case, those 2 are going to share properties of the main 3 anyway. So let's get into what makes up something a solid, a liquid, and what makes a gas. So first, let's talk about solids, okay? Solid is a state of matter that's defined as an object having a definite volume and shape. Okay, that means that the amount of space it takes up and shape are not going to change. That should make sense. The computer you're working on, or the desk that you're sitting at, or the couch, I don't know where you are. But wherever you are, those solid things around you, okay, they have a definite shape. That shape is not going to change that much. Okay, if you're working on your desk is going to be the same size, so take the same amount of space in that room. That's not really going to change. For volume, and the shape is not going to change either. So the amount of space it takes up, the volume is not going to change, and the shape of the object is not going to change. The easiest way for us to talk about the 3 states of matter is to talk about a substance that exists in all 3 states in our everyday lives, and that is water. So what are we talking about with solid water? We're talking about ice. And I told you that all the atoms in a solid, all atoms are in motion. That includes atoms in a solid. So in a solid, how are they moving? Well, the atoms are just vibrating in place. They're moving back and forth, right, in place. They're locked together. They're locked in that shape. They don't really have that much energy. And so they just kind of move back and forth and back and forth and back and forth. And this is because the amount of energy they have isn't allowing them to break the bonds that hold them together. Okay, so we're going to talk about chemical bonds later, but just understand things are attached to each other through chemical bonds. And those bonds can be broken given enough energy. But right now, the solid is the lowest amount of energy of any of the states of matter. And so they just have enough energy where they're moving back and forth and back and forth. And that's what this is trying to show up here, okay? The idea that they're moving back and forth. Okay, right here. Now, as solids are heated, remember, heat is a form of energy. So as you give something more energy, they're going to speed up. And what happens is if you heat something enough, what happens to it? It begins to melt, right? We're talking about going from a solid to a liquid. You give it enough energy, it begins to melt. So what does that mean in terms of the atoms? Well, means it's going to turn into a liquid. Okay, a liquid is defined as a state of matter that has a definite volume, but no definite shape. So what do I mean? Well, I mean a gallon is going to be a gallon, going to be a gallon. It doesn't matter whether it's in a jug shape, a pitcher shape, or a flat on the floor shape. Okay, so the amount of liquid doesn't change. All right. So you've got a cup, you've got a cup of water, you got a cup of water, you got a cup of water. It doesn't matter whether it's in a glass, whether it's in a measuring cup, or whether, again, it's spread out all over the floor. The amount of water doesn't change, but the shape does, right? When the water's in the glass, it takes the shape of the glass. When the water's spread out on the floor, it takes the shape of the floor, right? It gets real flat. So the shape is always going to change, but the volume doesn't change that much. And this is because the atoms have enough energy that they can actually slide past one another. They have enough energy to break those bonds that's locking them in place, but they don't have enough energy to escape completely, and that's the key. So we have enough energy, there's motion, they're sliding past each other, they're moving around. That's what this picture is showing us with all these arrows. These are actually sliding past and moving around, but they're not escaping away from each other, okay? They're still kind of stuck together. That water is going to be stuck to the rest of the water molecules. So this is the middle level of energy. So solids have the lowest energy. You add energy, they begin to melt, all right? And they melt into a liquid that has no definite shape, but a definite volume. Now, if I were to take away energy, if I was to cool that liquid and cool it and cool it and cool it, we already know what's going to happen. If you take away enough energy, the atoms are going to get locked into place again, aka they're going to freeze. So they're going to lose energy if you cool them. They're going to lose that energy. They're going to slow down. They're going to get locked into place, and they're just going to go back to vibrating, and that's going to be freezing back into a solid. So we can go either way here. We can go, add energy and cause it to melt, or we can take away energy and cause it to freeze. So it changes in state. Now, what were to happen to a liquid if we kept giving it heat, if we kept giving it energy? Well, the atoms would gain more and more and more and more energy, and eventually they would gain enough energy where they could break away from each other and evaporate into a gas. So evaporation is where a liquid changes to a gas. So what makes a gas a gas? Well, it's defined as a state of matter that has neither a definite volume or a definite shape. So it's got no set volume and it's got no set shape. The reason for this is because the atoms have a lot of energy. It's one of the higher energy level ones. And the atoms move very, very quickly. They move so quickly that they can actually completely break the bonds from each other and completely spread out to fill the space. So think about, the easiest way for us to think about a gas going into space is, think about like a scented candle. That candle is going to be placed in one part of the room. It's not just going to make that one part of the room smell good. It's going to diffuse. It's going to spread out throughout the room, throughout whatever space it has, and it's going to fill that area with that scent. So again, taking a liquid, adding energy, adding that heat, it's going to cause it to speed up. Eventually, those bonds are going to break away from each other. Now, what's really hard to think about is evaporation is actually a cooling process. So I want you to think about a pot of boiling water. As you heat a pot of water and it begins to boil, the temperature begins to rise and rise and rise and rise and rise until that water begins to boil and it starts to evaporate as steam. You kind of see that come off the water. But the key is that the energy that is being added stays with the molecules. So as they gain enough energy and as they escape that liquid water, they're going to take that energy with it. So it actually removes energy away from the water as a whole because it turns into a gas and it shoots out somewhere. Okay. So the key here is that making the overall pot of water have less energy. So evaporation is a cooling process. This is why when you get hot, you sweat. It's not to be cooled by the water itself. The water's coming out of your body. It's body temperature. It's hot anyway. What happens then is it evaporates into the air. And as that water turns into a gas and leaves your skin, it takes heat with it. And that keeps your skin a little bit cooler than it was before. So that's why evaporation and sweating is a cooling process, right? That water evaporates, it takes the heat away from your body. Now, again, we can go either way. So if we take heat away from a gas, it's going to condense into a liquid. So If we heat a liquid, it's going to evaporate into a gas. If we take heat away from the gas, it's going to condense back into a liquid because heat is energy. So if all atoms are in motion, we can add up that energy. I know we were talking about this in physics, but we talked about kinetic energy, the energy of an object in motion, the speed, right? And the key here is that kinetic energy, we can calculate the energy of large objects, right? We take the 1/2 times the mass times velocity squared, so that should have a squared right there, okay? We know that's the formula for kinetic energy, 1/2 times mass times velocity squared. So does gas have mass? Well, yes, it does. And does it have speed? Well, technically it does. I just told you that all the atoms are in motion. So how does it work for how do we measure the motion of atoms? Well, we actually already do this every single day. We just don't understand what it is that we're measuring, okay? All the atoms have mass, all the atoms have motion, therefore all the atoms have kinetic energy. And like I said, we already measure this every day it's being measured. So what are we measuring? How do we measure the energy of the atoms? Well, it's called the temperature, okay? When you're talking about temperature, you're really talking about the kinetic energy of its atoms. You're really talking about how fast the molecules are moving. The faster they're moving, the more the speed they're going to hit the object with, like a thermometer, and they're going to transfer that energy, right? Because when two objects collide, there's a transfer of energy. We talked about that in the energy unit, right, with kinetic energy. If they collide, they're going to transfer that energy. Go bowling, the bowling ball hits one pin, and that pin hits more pins. Again, that's all transfer of energy, and it's going to go so on and so forth. So if we take the temperature of an object, what we're really measuring is how fast those molecules are hitting the thermometer. Okay. Normally, I would do a nice little drawing here, which I can actually do. Let me switch over to the camera so I can show you what it is that I'm talking about. That's not the one. Choose virtual background. Please. There we go. So I'm going to stop sharing my other screen so you can see this a little bit bigger. Okay, so we can talk about how a thermometer works. So if I have a thermometer, and let's say I put the thermometer, now I'm not an artist, so please, no judging of my art here, okay? But let's say I had a beaker with water in it, okay? And in that water, I'm going to stick a thermometer. Okay, here we have our thermometer. So what's happening is this is a liquid, right? So the atoms are in motion, they can slide past each other if they have enough energy to do that. And so really there's all this little movement of molecules in random directions, all directions. Every once in a while, a molecule will run into the thermometer. And like I said, when objects collide, they transfer that energy. So the kinetic energy of that molecule is going to be added to the inside of the thermometer. And that speeds up whatever liquid we have in the thermometer. Right now, it's usually alcohol, right? A type of alcohol. We don't use mercury anymore in thermometers because mercury is toxic. Thermometers can break easily, especially if they're glass. So what happens is the atom runs in there, it transfers some of that energy, and that increases the energy in the thermometer. What does that do to that liquid? Well, it gives it more energy, so it takes up more space, and so it expands. And so that's going to cause the thermometer to rise, right? Now, let's say we put in some ice cubes. Okay, I don't know why my ice cube is going halfway out the glass, but just deal with it. So I put in some ice. Well, what's that going to do? Well, it's going to slow the molecules down. All that heat is going to be transferred into the ice cubes, it's going to speed up those ice cubes, and they're going to melt. But overall, it's going to slow the motion down in the entire beaker itself. So that means that the molecules inside of the thermometer are moving faster. So what's going to happen? Well, they're going to hit the side of the glass, just like the water did on the outside. It's going to transfer some of that energy outside of the thermometer, right? That energy is going to be taken away by the cooler water. That's going to cause these molecules to lose energy inside the thermometer. They're going to contract. They're going to take up less space. So that line drops, and that indicates a lower temperature. But it all has to do with the speed of the molecules, how they're moving and how they're running into things. So temperature is really a measurement of the speed of the molecules. Let's go back to the PowerPoint. So unfortunately, because it is what it is, we have three entirely different temperature scales. Now, you're going to hear a little bit of my bias here because there's one scale which is the one that we should be using, there's one that we do use, and then there's one that mostly science uses. But we'll get into that. Hopefully my bias won't come through too much, but you'll hear it in a minute. First off, let's talk about the one that we're most comfortable with here in the United States, which is the Fahrenheit scale, okay? The Fahrenheit scale was introduced in 1724. We realized that we needed a way to measure things, and this is again when metric system was still being formed and whatnot. And so we had a whole slew of different temperature scales coming out at the same time. Some of them took hold, some of them did not. But Fahrenheit was one that did take hold, and it was defined by two fixed points. Again, based on water, but not necessarily. The scale was made first, and then they figured out where water was. So on the Fahrenheit scale, water freezes at 32 degrees and water boils at 212 degrees. Now, my question for you is why? Why 32 degrees? Who decided that? Well, again, it's because of the way the scale was made. The scale was made first, the gradations were made, and then they were like, oh, let's figure out where water does stuff, right? Because that's the most important, one of the most important components of our planet, liquid water. So then they found out, oh, it freezes at 32 degrees and it boils at 212. But again, those are not easy numbers to work with, right? And it's really just frustrating the United States uses this because, again, this is not the metric system unit. This is one that was made outside of the metric system. The metric system uses the Celsius scale, which we'll talk about in just a second. But again, we have arbitrary points, right? Just kind of like we talked about how many ounces in a cup. Why is that a cup? Why is it 8 ounces? Like, seriously, like, who determined this stuff? How to measure it? Doesn't work on any powers of 10 or anything like that. So it is a bit arbitrary. So this guy, Fahrenheit, named that for himself, obviously. Not necessarily the best scale, but it is the one that we use here in the United States. The much better scale is the Celsius scale, okay? After they realized the Fahrenheit scale kind of got things backwards, where they thought of water as more of an afterthought, the Celsius scale is based on water. And that's really an important thing for our planet. So it makes sense that our temperature scale should be based on water. What they did was they said 0 is going to be where water freezes. We're going to make 100 degrees where water boils. And we're going to just make even gradations in between the two. So water freezes at 0 degrees Celsius, it boils at 100. That makes much, much, much more sense than these two random points of 32 and 100, 212. Again, 0 to 100, right? Very simple to follow. If it's 0, it's freezing. If it's 100, it's boiling. So 100 or higher, it's boiling. There is a theoretical state in science. So Celsius works great for biology, right? Most sciences, you're just talking about, normal temperatures between those two, or maybe a little bit above or a little bit below, but not too much drastic outside of that. But when you're talking about science, you're talking about, chemical reactions going on inside of stars or things like that, or you're talking about the temperature of space. It really gets kind of very extreme on the Celsius scale because water has a pretty narrow window when it's, solid, liquid, gas. So obviously there need to be a bigger scale to be able to take into account things that are colder than 0, that are much, much colder than 0, which is a theoretical state we call absolute 0. And we also needed a scale that went up much, much higher than the Celsius scale, numbers that made sense to talk about the temperature of stars and things like that. So that's when we came up with the Kelvin scale, which is really, really, really just an expanded Celsius scale. There's not really, all the gradations are equal. So that's really important. The differences between the degrees are equal. But instead of starting 0 at where water freezes, the Kelvin scale goes all the way down to a point we call absolute 0. So remember when I said all atoms are in motion? Well, that absolute 0 is the theoretical point where you take away enough energy that the atoms actually lock in place. They're actually not in motion. Now, here's the issue, is we know heat moves from areas of hot to areas of cold. So absolute 0 is a theoretical point. We haven't actually found absolute 0 in the universe, right? Because the Big Bang released a lot of heat, and that heat is still traveling all over. So anytime a place would, be cold enough to get to absolute 0, heat is going to travel into that area from the surrounding area because it wants to move from higher concentration to lower concentration. So hot to cold. So there's no real absolute 0 that we've found in nature, basically. We've not been able to achieve absolute 0. So if you compare, absolute zero is about negative 273 degrees Celsius. Remember, water freezes at zero. So absolute zero, you can see, is much, 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 much colder. Space is usually sitting at around negative 270 degrees Celsius. So about 3 degrees Kelvin is the temperature of space. Now, because we have all three of these scales, Celsius being the best and the one we should be using, Kelvin being second best, and the third, bringing up the rear, the one that we're stuck on, degrees Fahrenheit. Because we have all three of these scales, we actually have to know how to convert between the three scales. I'm going to tell you, the conversion between Celsius and Kelvin is very easy because they work on the same set of interval, right? The same gradations. So because this one is just set to a little bit lower, the conversion between these two is very easy. Converting between Fahrenheit and Celsius or Fahrenheit and Kelvin gets much, much more complicated because this scale just is set up entirely different from the other two. But we need a way to compare them, and because we can't quit the Fahrenheit habit, we'll have to figure out how to convert these. So here are two formulas that are going to be added to the formula card for your use. What we are converting to needs to be on the other side of the equal sign, and what we're converting from needs to be in the equation. The hardest thing people get tripped up on converting between temperature scales is just figuring out which one to use. Whatever you're going to needs to be on the other side of the equal sign. So if I'm starting in Fahrenheit right here and converting to Celsius, what I have to do here is I have to take the degrees Fahrenheit minus 32 times 5/9. Okay, so order of operations says you got to do this first, take the degrees Fahrenheit minus 32, and then your calculator, that can come second. 5 divided by 9 times whatever this number is. And you'll get that in degrees Celsius. If for whatever reason you need to work backwards and convert Celsius into Fahrenheit, the equation changes a little bit. Okay, and notice the parentheses are different as well. So order of operations says we would do what's in the parentheses first. So you take 9 divided by 5 times the degrees Celsius, and then at the end you add 32. So you really have to be careful. That's another mistake I see people make. If they choose the right one, the second mistake that they sometimes make is they don't do the order of operations correctly. And so we'll go over a couple of these to make sure that we know how to do them on the practice as well. And like I said, converting between Kelvin and Celsius is very simple. If you're going from Celsius to Kelvin, all you have to do is take Celsius and add 273. How simple is that? Simple addition. If you want to go the opposite way, what do? Well, you subtract 273. All right, very, very, very simple because, again, these two scales work on the same interval. So this is a very easy conversion. As you can see, this is a nightmare. This is no fun to do. These conversions are not good, so we should just quit the Fahrenheit habit. Oh, there's my bias. Okay. All right, so if we're going to practice that, what we need to do is convert 32 degrees Celsius, 32 degrees Fahrenheit, rather, excuse me, into degrees Celsius. So we're going to go from 32. I'm going to pull up my camera. So we're going to go from 32 degrees Fahrenheit. And we want to convert that into degrees Celsius. Okay. I'm going to pause the screen share so I'm going to move the screen back so we get our formula. So which one are we going to be using? Well, we're starting in Fahrenheit and we're going to Celsius. So we're going to actually be using this one right here. I don't know if you guys can see that or not. If I move that camera, I don't know if that helps you guys or not. But in any case, we're going to be using this top one, all right, going from Fahrenheit to Celsius. Okay, so degrees Celsius equals 5/9 times the degrees Fahrenheit minus 32. All right, this one should be easy. I'm going to stop the screen share so we can just see the camera up nice and large. Of course, I'm running at an angle again. All right, so now I plug in my numbers. So 5/9 stays 5/9. I plug in my degrees Fahrenheit, which is 32. 32. So 32 minus 32 is going to give us 0. We know anything times 0 is 0. So we should have that with 0 degrees, and the new one is Celsius. Why does that make sense? That should make sense because we know 32 degrees Fahrenheit is where water freezes, 0 degrees Celsius is where water freezes. So this is showing us how we got to that number. That conversion. All right. And if we convert 32 degrees Celsius into Kelvin, this is a much, much simpler one. All right, so we're going to take 32 degrees Celsius, convert that into Kelvin. Okay, so again, I'm just going to open up the slide with the formula so we can see it here. Here it is, very, very simple. So we have Kelvin equals degrees Celsius plus 273. Now it's important to understand, we just say Kelvin. There's no degrees Kelvin. It's just whatever the number is and then Kelvin, because it's not split up the same way. We would say degrees Celsius, degrees Fahrenheit, but you would just say whatever the number is in Kelvin. So we plug in our number here. I'm not going to make the screen big. This is a simple addition. And I take 32 plus 273. That's going to give us 305 Kelvin. All I did was add these two in my head. 3 plus 2 gives us 5. 3 plus 7 gives us 10. 0 to the 1. Wind up with 305 degrees Kelvin. All right. Now, if I wanted to convert 32 degrees Fahrenheit, we already did that one. Sorry. If I wanted to convert 580 degrees Fahrenheit into Kelvin, now, if we notice, there's not a direct step from Fahrenheit into Kelvin. We talked about going from Fahrenheit to Celsius, and we talked about going from Celsius to Kelvin. So this is actually going to be a two-step process. So we need to go 580 degrees Fahrenheit and to change that into Kelvin. So again, this is a two-step process. So what we're going to start with is we're going to use this top one. And we're going to go degrees Fahrenheit into Celsius. And once we have Celsius, we're going to go one step further and convert that into Kelvin. So let's start that here. So degrees Celsius equals 5 over 9 times the degrees Fahrenheit minus 32. Okay, let's stop the share so you guys can see this camera a little bit bigger. Okay. See my end of parentheses. So now I'm going to plug in my number. So 5 over 9 is going to stay 5 over 9. I have 580 minus 32. Okay. So if I take 580 minus 32, I end up with 548. So 5 over 9 stays 5 over 9. Now in the parentheses, I have 548. Okay. So the easiest way to do this is in your calculator. This is now all division and multiplication. So you just work from left to right. So what I'm going to do is I'm going to, in my calculator, take 5 divided by 9, get the equal sign. You should end up with 0.5 repeating. This is why it's important to plug it into your calculator, because without that repeating, it could really affect how many degrees you're off by. So 5 repeating is 5 over 9. I'm going to take that in my calculator and I'm going to multiply that answer by 548. And I end up with 304.4 repeating. So I now have this in degrees Celsius. So now we can go one step further, right? Because we know we can take Kelvin equals the degrees Celsius plus 273. That's from the formula. So now I can plug in this number. So I've got Kelvin equals 304.4 repeating plus 273. So we're going to take our answer plus 273. And we end up with, hey, look at that, 577.4. So 580 degrees. So this is where both the Fahrenheit scale and the Kelvin scale kind of line up. We started with 580 degrees Fahrenheit, and we ended up with almost 580 degrees Kelvin as well. Okay. All right, so now what I would like you to do is I would like for you to pull up the temperature scales practice, temperature conversion worksheet. Stop the camera. Let's see which screen I share. Make sure you guys have the right screen. Okay, there we go. All right. So what you guys have is I've broken it up. In the top section, you're going to convert the following into Fahrenheit. So I see here degrees Celsius, converting that into degrees Fahrenheit. The second section, you're going to go from Fahrenheit into Celsius. And the third section, you're going to go from Celsius to Kelvin, and then from Kelvin back to Celsius. Okay, so let's do one from each section, and then I'll set you guys loose. Sheet paper. Now let's take a look at the first one. So the first one, we're starting with Celsius, and we're going 2 degrees Fahrenheit. So this one, I'm actually going to be using the second formula. Let me just pull that up real quick so you guys can see that. All right, so we're going to be using this bottom one because we're starting with Celsius and we need to get to degrees Fahrenheit. So I'm going to write that formula at the top. You guys can see that. Okay, there we go. So we're going to be using the bottom one, degrees Fahrenheit equals 9 divided by 5 times 2 degrees Celsius plus 32. So stop the share so we can see. Going back to the assignment, we need to go from 10 degrees Celsius. So 10 degrees Celsius, and we need to turn that into Fahrenheit. So this is why I'm using this formula, because if you guys look again, the degrees Celsius is in the problem. Degrees Fahrenheit is on the other side of the equal sign. So I know what I'm converting to needs to be over here. So I'm going to plug in my numbers. So 9 over 5 is going to stay 9 over 5 times my 10, which is my degrees Celsius, plus 32. So in my calculator, I'm going to take 9 divided by 5. And what's nice about this one is it is an even number. It's actually 1.8. So I take 1.8 times 10, right? And what that is going to give me is 18. I know if I'm multiplying by 10, I can just move that decimal place 1, right? Plus 32. So now I add in that 32. And I come up with an answer of 50. So 50 what? 50 degrees Fahrenheit. So when it's 10 degrees Celsius outside, that might, oops, sorry guys, didn't realize it was the bottom of the camera. So when it's 10 degrees Celsius outside, that might sound cold, but it's actually 50 degrees, which isn't too bad, especially considering what temperatures we're having lately. I would kill for 50 degree day. All right, so that's how to go from Fahrenheit to Celsius. Again, what you want to focus on is the order of operations, right? So do this first, then multiply by this, and the last you're going to add in that part. All right, multiplication, division happen at the same time, so just left to right. Addition happens after that. If we jump down to the next equation, the next section rather, we're going to convert the following into Celsius. So we're starting with degrees Fahrenheit, going to Celsius. Again, that's degrees Celsius equals 5 divided by 9 times the degrees Fahrenheit minus 32. I'm going to be looking at number, let's not do number 6. Let's do number 7, because we already did number 6 in the example in the PowerPoint. So I'm going to do number 7, which is asking us to convert 45 degrees Fahrenheit into degrees Celsius. Okay, that's what we're going to be doing with this problem. So now I plug in my numbers. Okay, so 5 over 9 is going to stay 5 over 9 times my degrees, which is 45 minus 32. Okay, And if I take 45 minus 32, I come up with an answer of 13. I'm just going to drop down my 5/9. So now on my calculator, again, because I want that repeating decimal, I'm going to take 5 divided by 9, hit the equal sign, that gives me my 0.55555 repeating, times 13. And I come up with an answer of 7.2. It is 2 repeating. You could put that if you want. I'm not going to mark it off. As long as you're close enough, I will be happy. And that is now in degrees Celsius. So there is our final answer. Again, following order of operations, you have to do the subtraction first. That's in parentheses. Then the division and multiplication from left to right. The next two examples are quite easy. Let's jump down to number 13. Number 13 asks us to convert degrees Celsius into Kelvin. So Kelvin equals the degrees Celsius plus 273. Sorry, I was already thinking about that 7. 273. There we go. Number 13, like I said, asks us to convert negative 50 degrees Celsius into Kelvin. So I'm going to plug in negative 50 plus 273. So when I'm adding a negative to a positive, it's really like subtracting, right? We're taking that away. So we're going to end up with 223 Kelvin. So that's simple. Okay, jumping down to the last section, we're looking at number 16. Number 16 is asking us to go backwards from Kelvin to Celsius. Now, I didn't give you a formula for that just because this formula is very simple. If I want to isolate the C, how do I undo addition? I just subtract, right? So degrees Celsius is simply Kelvin minus 273. So like I said, we're doing number 16. So we're going to convert 100 degrees Kelvin into Celsius. So I have 100 minus 273. Notice the negative is on the bigger number, right? The minus the bigger number. So we should come up with a negative answer here. And we do. We come up with negative 173 degrees Celsius. Because I just took 100 minus 273. All right, so that's one example from each section. You guys just have about 4 or 5 other examples, maybe 3, somewhat less, depending on what section it is to finish up. Again, I'm just working off of this paper right here. So we've done number 1, we did number 7, we did number 13, we did number 16. So you just have the rest of those to finish up. Once you get those done, make sure you submit that to me. And then again, lastly, take a look at the class, okay? You also have the States of Matter exit ticket, States of Matter X ticket right here, so that Google form. Click on that, answer those questions. All right, same thing we've been doing, and get that submitted as well. Again, just a final reminder, if you have not taken the quizzes, so that's the week 1-2 quiz, the week 3 quiz, or your midterm, please get those done as soon as possible. I cannot ask you or beg you enough. The sooner you do them, the fresher they are in your mind, the better chances you are going to have of passing them. So, and remember, you can take them more than once. So take it once, get it under your belt. That way you can be ready to go for the next one. Okay? If you have any questions, comments, or concerns, don't hesitate to reach out. Remember, nick.welsh@excelcenter.org is my email. You can message me on Gmail. You can Facebook me, Tech Nick, or Tech Richmond Nick. I don't know what's my Facebook. That's my work Facebook. Yeah, Tech Nick, what it looks like. Okay, you can find me on here. Tech Nick Welsh, there we go. Okay. And that's where I put all my announcements and stuff, but I also get messages and stuff through there. So if that's easier, please don't hesitate to reach out. I'm here to help. I I'll be Zooming again tomorrow, same time, 10:30. So pop in, say hi, ask questions, get caught up. We're moving on with chemistry. So tomorrow we're going to start talking about the atom. So we got to make sure that we are up to date on all the stuff and ready to go. Otherwise, good. Guys, have a great day, and I hope to see you on Zoom tomorrow.